Hi everyone. In this video, we will see the voltage vector selection for DTC control, and we will understand that how taking the appropriate voltage vector increases the stator flux as well as the torque. So let's begin. So as we have seen in our previous video that DTC directly controls the torque and the flux, and it also does not require the paths transformation and the DQ transformation, the class transformation, and the paths transformation explicitly. So therefore, it is computation where it is very simpler as compared to my FOC control. So here we can see that it directly estimate what is the stator flux and what is the torque estimator by taking the feedback of my voltage vector. So here this is the voltage vector of the stator and the motor currents. So by taking that, it calculates the stator and the stator voltage and the current space vector, and based on that, it compares the actual torque running and the reference torque requirement, and it creates the error which is del tau and the del phi s. This is nothing but the stator flux vector. And here, based on the voltage vector selection, which we are going to talk about in this video, that how to select a voltage vector, which is nothing but it is also known as lookup table. So based on this predefined lookup table, it performs the switching of this inverter. So the switching of this inverter happens based on the lookup table, and the lookup table decides based on the generated error over here. So therefore, this kind of a switching is known as my space vector modulation, it also known as SVM. So therefore, unlike in the FOC that it requires the or it uses the PWM inverter, so my DTC control mostly works on my SVM or the space vector modulation, and this is nothing but how the voltage vector controls my stator flux and how it also controls the torque. So based on that, the voltage vector has been selected, and then it controls the speed and the torque of my motor. So this is nothing but the AC motor. It can be induction motor, it can be PMSM motor, and it can be my synchronous reluctance motor. So to understand the voltage vector generation and how the space vector is applicable to increase or decrease the torque, similarly increase or decrease in the flux. First, let's understand the working of my two-level inverter, and through that we will understand that how the space vector generation is been created. So this is nothing but the two-level inverter. Three-phase bridge converter is taken over here, which is nothing but the two-level inverter, and here the input voltage is, let's say, the VDC, and then we have the six switches over here. So we have S1 to S6, and my three-phase motor is being connected through this. And for this inverter, the voltage vector has been created from V1 to V6, which is the six vectors we have, and the remaining two vectors are the zero vectors. So all these vectors are being generated through the switching of my inverter switches from S1 to S6. So how these switches being responsible to create the flux vector or the voltage vector, like here this from V1 to V0, we can see that this is these two uh, voltage vectors are being spaced by 60 degree, and similarly we have six vectors which all are apart with the 60 degree and being created the whole space vector over the 360-degree angle. So let's understand the switching. We'll take an example that how one switching is being created and then how the voltage vector is being generated. So now let's understand that how the switching combination can create my different voltages vector. So we know that for the three-phase inverter, the output voltage can be represented in terms of the space vector. So this is my voltage space vector, which coming equals to 2 by 3 VA plus VB is for J 2 by 3 and similarly VC. So this is nothing but my operator, and it is being represented in terms of my rectangular form. This can also be represented in the polar form, that 2 by 3 which is the VA plus VB at an angle of 120 degree plus VC at an angle of 240 degree. So where the VA, VB and VC are my phase voltages. So let's understand that how a switching states generates my voltage space vector with different angles. So let's understand the voltage generation from a two-level inverter. Let's say this is my input VDC and I have six switches. It can be in the form of IGBT or the MOSFET. So if this switch is, let's say, SA, then the state of this switch is SA dash. Similarly, for the second leg, let's say if this is SB, then the status of the same leg switch is SB dash. And similarly for this switch also, the third leg is SC and SC dash. Or I can also say that switch number 1 to switch number 6. If the state of this SA switch is 1, then uh, it says that the switch of the same leg AC dash will be 0, just to avoid this short circuiting. And this is my A phase, this is the point of B phase, and this is the point of C phase. So now let's consider the voltage vector V1, which has the switching state 1 0 0. So if this happens, it means that SA is state 1, which is this switch is closed, and 0, that means the SB is open, and then SB dash becomes 1, which this is also closed, and similarly SC dash is also closed, and therefore the output of my VA becomes VD dash, and similarly the output of VB also becomes my, and VB becomes this also 0, and the VC becomes also 0. So therefore, if I have to create voltage space vector, which is nothing but 2 by 3 of VA plus VB at an angle of 120 and VC at an angle of 240. So putting the value of VA, VB, VC, I have VS is equals to 2 by 3, and this becomes VDC, which is nothing but I have a vector this 2 by 3 VDC, which is equals to VS. So this becomes the voltage vector V1. It's having the value of 2 by 3 VDC at an angle of 0 degree. Similarly, if we will look out for the state 2, where the switching sequence is 1 1 0, which means that the state of SA is 1 closed, SB is also closed, and SC dash is 1, not, and SC is 0. So therefore the output voltage VA will be VDC, and VB is equals to VDC, and VC becomes 0. And finding on the state vector, this has to be multiplied with the 2 by 3. So putting the value of VA and VB over here in this equation, we have the space vector Vs is equals to 2 by 3, putting the value of VA, which is VDC, and plus putting the value of VB, which is VDC, and then the operator, which is at an angle of 120 degree. So this is nothing but 2 by 3 and VDC, and plus opening this VDC cos 120 becomes my minus 1 by 2, so minus 1 by 2 VDC, and plus J sine 122 becomes root 3 by 2 VDC. So this is root 3 by 2 of this VDC. So this becomes half of VDC, and this becomes J root 3 by 2 VDC, which is nothing but the Vs vector becomes equals to 2 by 3. Taking VDC also common over here, then we have half plus root J root 3 by 2, and VDC has been taken out. So this is nothing but in the rectangular form. Converting this into the polar form gives us the value of VDC into 2 by 3 at an angle of 60 degree. So earlier for the state 100 we have seen that it was at angle of 0 degree. The same for the 110, it has moved with the angle of 60 degree. So overall, the space vector can be determined directly with this formula based on the state of my switches. This E or VDC, which is nothing but the input to my inverter. So this defines this the space vector for any switching combination. Let's say I have switching combination 0 1 0. So in that case, the space vector Vs will be equals to 2 by 3 the VDC, and SA becomes 0. SB is the only one, so this becomes again at at an angle of 120 degree, and SC is also 0. So that becomes my the space vector for 0 1 0. So therefore, if we will see the switching of switching combination of my switches, so how the space vector moves with respect to angle, this can be imagined with this figure. It is clearly stating that that how a different combination of switching moves my voltage vector in space. So this shows that if the state is with 0 1 0, then what are the switching is happening, and what is the angle of my voltage vector is occurring. So to conclude this space vector, we can see that how the different combination uh, creates my different voltage vectors. Like 0 states has the output voltage 0 0, so this is known as the zero space vector. And similarly the V1 V2 how they are moving with an angle, and then this is nothing but the similarly it is shown over here that this is the V1, this is V2, which is apart with the 60 degree having the same magnitude, and similarly V2 and V3 again they are apart by the 60 degree having the same magnitude, and similarly all the space vector with each other are spaced 60 degree. This V3 and V4 again 60 degree, and V4 to V5 again 60 degree. So this creates the whole space vector on my 360 degree angle. And now creation of this space vector, which is happens through inverter, how it leads to increase or decrease in the torque, similarly how it uh, responsible for increase and decrease in the flux, that we need to understand now. Now let's understand how the flux and the torque variation happens. So I'm taking an example of the induction motor case over here. We know that the stator voltage Vs is equals to the drop in the stator, which is Is Rs, and plus d phi by dt, d phi s by dt. So taking that into account, I can say that the stator flux phi s is equals to Vs minus Is Rs and integration of it. So this expression is being used over here, and it has been shown in on the DQ frame. So this psi d is nothing but the direct axis, where the direct axis voltage VD minus RS into the direct axis current has been taken into account, and dt, and similarly the q axis flux is equals to the q axis voltage minus rs q axis current, and then dt. So we know that the direct axis and the quadrature axis, they are uh, nothing but 90-degree apart. So therefore the total stator flux is nothing but the direct axis stator square plus the quadrature axis stator square and under root of it. Similarly, the torque which is being produced by the induction motor is equals to 3 by 2 number of poles, and the flux and multiplication of flux in the current, the direct axis and the quadrature axis current, minus the quadrature axis stator and the direct axis current. We also have I'm just elaborating this torque phenomenon, torque expression over here, so that we will have the better understanding that how torque can be varied by varying the angle between the stator flux and the rotor flux. So any stator flux vector variation determines a torque variation on the basis of two contributions. One is the variation of the stator flux magnitude itself, and the other one is the variation of stator flux phase angle with respect to rotor flux. We know that the stator flux always lead with the rotor flux. If this is my, let's say, the stator flux, then the rotor flux will always lag by some angle. Uh, this angle is nothing but the theta SR. So here I can see that this expression shows the my rotor flux, and which depends on the mutual inductance and the stator inductance, and also 1 by S rho tau r into stator flux. So this rho is nothing but again a constant value, which is 1 minus Lm squared divided by Ls into Lr, whereas the torque is being developed is equals to 3 by 2 into P, which is number of poles, and again this value becomes constant into the stator flux vector and dot product with the rotor flux vector. So elaborating this expression, we get that the torque depends on the angle between stator flux, rotor flux, and the angle between that. So it depends on the magnitude also of my stator and rotor flux, and it also depends on the angle between the my stator flux and rotor flux. So therefore these two variation can be happen that directly, which depends on the stator flux magnitude. So if I'll increase the phi s directly, it will increase my torque. Similarly, if I can increase the angle this theta SR, then also it will increase my torque. So the variation happens based on these two contributions. So now let's see that how choosing the right vector can increase my torque and the flux. So let's understand that this is the estimated stator vector, which is shown over here. So this is the estimated state vector or the actual state vector of my running motor. So based on the error generated by the comparison of torque and the flux estimator, let's suppose that I need to increase the torque. So if I need to increase the torque, I need to increase the angle between the stator flux and the rotor flux vectors, which is the theta SR. So let's say if this is the stator flux vector, which is shown over here, currently this is the present stator vector. So if I choose the vector of, let's say that V2, which is 110, and for a shorter period of time, let's say the del t. So by choosing this, I can say that the actual vector now becomes a resultant of this. So the angle is being increased. So my stator vector gets moved ahead by this angle, which is more than the previous angle. So by choosing the right vector, I can increase the torque. Similarly, if I increase, if I choose the vector, let's say uh, v3, so in that case, this vector and this vector again gives me the increase in the angle theta SR. However, it also reduces the amplitude of my flux vector of state of which is phi s. So let's say I have a condition where I need to reduce the stator flux magnitude, but I need to increase the torque. So therefore, I will choose the vector v3 as per the current vector. So this was the current space vector which I have estimated through my estimator. This vector is continuously moving, so therefore, the as per the current vector uh, which is estimated through the feedback, and according to the requirement of the by the error generation, I need to select the proper vector. So this table gives me the comprehensive idea that which vector needs to be selected. So let's say that I need to increase the flux, and I also need to increase the torque. So if my actual vector is remains, or it has been identified in the sector 1, so therefore I need to choose the voltage vector V2. And if it is in the sector 2, then I need to select the switching vector V3. Similarly, if it is in the sector 3 or segment 3, then I need to select the switching combination of V4. Similarly, if I have to reduce the torque and for increasing the flux, if it is in the segment 1, then I need to select the vector V6. If it is in the segment 2, then I need to select the switching combination V1. So it goes like this for the different segment. What I need, if I need to increase the torque or decrease the torque for increasing flux. Similarly, let's say I need to reduce the flux and I need to increase the torque, and if it is my actual vector is in the segment 1 or the sector 1, then I need to select the switching vector V3 combination. If it is in the vector segment 2, then I need to select the switching vector V4. So this table helps to identify, based on the requirement, whether I need to increase the flux or increase the torque, or I need to decrease the flux or decrease the torque, and my actual state vector, in which segment it lies in amongst the given six segment or sectors. Then accordingly, this table helps to identify which a combination of this, which switching combination needs to be select, and based on this lookup table, the switching of my inverter happens, which is known as the space vector modulation. So through this video, we have understand that how the voltage vector is being generated by an inverter switching combination. And here in this video, we have taken an example of two-level inverter, and we have seen the switching combination and then how it generates the output voltage vector. Similarly, how to choose those vectors based on my requirement, whether I need to increase the torque or decrease the torque, and similarly for the flux, the lookup table has been created, and based on this lookup table, the switching combination of the inverter can be identified, and which in turns controls my motor torque and the speed. So this is all about the DTC control, and I hope we have understood that how the DTC is more simpler in terms of the computational than the FOC. Thank you.